So in this part, we're going to continue off where we left from to mesh our geometry. So we've added our physics and everything, defined our material parameters and average operator on the water interface. So for the meshing system, what we're going to do is we move to the mesh, and under the physics controlled mesh section, and we have the element size. We'll be using the extremely cost. Okay, so you right click on the mesh and we select the edit physics induced sequence, which will give us a free tetrahedral, corner refinement, boundary layers, and so on. So under the free tetrahedra, under the scale geometry section, in the X direction will be 0.5, and the boundary layers locate the boundary layer properties. Okay, so under the number of boundary layers, we change it from 5 to 3, and under the thickness adjustment factor, we change it to 2. Then we build all. Okay, so now we've meshed our work. We can go on to compute. This will take some time, a while to compute. So after it computes, we're gonna have a slice plot of the velocity field. We'll also do a plot of the contour pressure and surface plot of the wall. Even after we get our results, we would go and try and get some plots. We'll try and get some surface plots and some 3D plots. So it depends on how fast or slow your machine runs. It could take shorter time than mine, or it could take longer than mine. I think this is going to take quite some time, so now after 48 minutes, 13 seconds of our time, our results are done. We've done computing. Okay, so let's expand the wall resolution as the SPF node. And okay, we have the interior walls. We have the temperature surface as well. And we have the isothermal isosurface. As you can see in here. So this under the wall resolution, interior walls, let's right click and delete this part. And we go to the surface. Okay, so now under wall resolution SPF, right click and we add a surface. And we choose the interior walls. And under the expression, we're going to type the SPF delta W underscore U. So you can see that we have our plots. Yeah, so it shows the surface of the interior walls. And okay, let's move to the next part. Go to where the temperature is. We select surface, locate the expression, and we want degrees Celsius. And we locate the range section. Select a manual color. Minimum, let's make it 65. Maximum, make it 80. Okay, so we expand the surface one node. Let me go back and let me redo this again. Okay, so at the surface, locate the expression here, make it degrees Celsius. Degrees Celsius. Sorry. Sixty-five to 80. And we move to the selection. Boundaries. I'm gonna select some boundaries. Okay. Let's select I'll select boundary 1, boundary 9, boundary 332. Move to the surface 2 and locate the expression. Select degrees Celsius for the units. And move to, okay, so move to surface 3. And the expression, we got surface 2, got surface 3, so 2, 3 degrees Celsius, degrees Celsius. Okay, so over here we have to get to temperature, and here we select as degrees Celsius. And what we'll do is plot we select from the results, we go to more data sets. We go to the results and we look for more data sets, and we select mirror 3D. Okay. So in the setting window for the mirror 3D, what we'll do is for the plane data section, we select the ZX plane. That's what we're gonna do. We select the ZX plane. And we add a 3D plot group. And we type velocity, velocity. Seamless, the streamlines. Yeah. And we find the data selection. Choose the mirror 3D that we used. Okay. Locate the streamline. Another streamline. Locate the streamline positioning. And where we have our points, we make 100. Okay, the coloring and style. So the line style subsection, we use a tube. Okay, so under the streamline, you look for the color expression. And for the color expression, so you place this expression under the heat transfer in fluids, under the temperature. Just locate the coloring and style. And under the color table, we use thermal. Okay. As you can see, it shows the thermal distribution in the shell tube heat exchanger. What we'll do next is we want to evaluate the equivalent heat transfer by coupling operators. So under the results, we're going to use a global evaluation. Okay, so we have a global evaluation, and the label field, we will type in heat transfer coefficient in the in the shell and tube exchanger. Okay. Locate the expressions. We have to input. Remember this operator definition that we did over here. We're going to input it here. That will compute our results. So that's this expression on ABS I T F1 F U, two brackets closed, then temperature of the water minus temperature of the air. You get this unit. So this variable will compute the heat flux through the wall. And now we click on evaluate. evaluate. Okay, so now that we've done that, go to results and you select more derived values. Under the more derived values, you're going to choose the average surface. Or the average, surface average. And under the label, we're going to name this as the inlet pressure. Water. And we're going to select the inlet select inlet water. And we're going to change the expression in here. We're going to replace this expression in here by going to our component tab under turbulent flow. We have velocity pressure. And we have pressure Pascal. And we evaluate. Okay, so now under the results again, we find more derived values and also the surface average again. That will be the inlet pressure. Inlet pressure. And another selection is going to be the inlet air. And we're going to replace the expression. Like velocity and pressure and evaluate again. Okay, so now go to the table window. Okay. So now you've been able to determine the pressure at the differential parts. You know the pressure at this part. That's the inlet pressure, which is about 38. We know where the water will be and where the inlet pressure of the air too as well, which is 9.2 pascal. So being able to evaluate all these areas where the tube side pressure, we have 38 and 9. So inlet for water, air, and we have this as well. Also seeing the streamlines. So also seeing the pressure in the walls. And other thermal values, like reading the okay. So this brings us to the end of this part. Later, I'm going to show you how we do this geometry. But if you have any questions regarding this, kindly let me know in the comment section and I'll do well to explain everything to you. So I'll see you in the next video and thank you.